Hello, AP Stat students. Today we will do 12.1a notes and a part of 12.1b. But before we do that, I'm going to go back to reviewing a little bit of Chapter 3 on scatterplots and linear regression. Scatterplots allow us to visualize the relationship between an explanatory variable and a response variable. Your explanatory variables, the x-axis variable, and the response variables on the y-axis. The correlation R allows us to describe how closely the data fits a linear pattern. So the correlation tells us if there's a relationship between the two variables, not causation, but relationship. Correlation values are always between -1 and 1. If R is equal to -1, then the data forms a straight line with a negative slope. If R equals 0, the data is truly a random pattern and does not come close to forming a line. And if R equals +1, then the data forms a straight line with a positive slope. Then we learned about least squares regression line, and this is known as the line of best fit. A regression line takes the data and summarizes the relationship between the explanatory and response variable. It is usually used to predict the value of the response variable. You will see the linear regression form in many different ways. You can see it as y equals a plus bx, y equals alpha plus beta x, and y equals b naught plus b1 times x. They're all the same. This is the one that's represented on your formula sheet. Where a, alpha, and b sub 0 represent the y-intercept. And then the interpretation of the y-intercept is, it is the response variable's value when the explanatory variable's value is equal to 0. So when x equals 0, what is the y value? And that's your y-intercept. And it might not always make sense in context of the problem, so you need to make sure that you're looking at that. And then b, beta, and b sub 1 represent the slope of the line. And the interpretation of the slope, and students miss interpretations a lot, and so this is a good review of going back to interpretations. So the interpretation of slope is the amount the response variable changes for each increase of 1 in the explanatory variable. Explanatory value, sorry. So you have this number increasing for every one value for the explanatory variable. And you know slope is rise over run, or the change in y divided by the change in x. So that's where you get that. And we talked about residuals. A residual is the difference in the actual response value and the predicted response value for a certain explanatory variable. And the way that students remember what a residual, how to calculate a residual, and this is super important, is just think of AP. It's actual minus the predicted. So if you remember AP, which you should, it's A minus P. So the residual in variable form is equal to actual would be Y minus predicted is Y hat. It's been a while since we've done this, but good review. The purpose of the regression line is to make the squares of the residuals added up as small as possible. And we do the squares because you're going to have some positive and negative values. You square them, you sum them up, and it's going to be close enough to 0 so that you have the best line, the line of best fit, and the best one. The residual plots tell us if a linear model is appropriate. It's for the prediction, if it's appropriate for the prediction equation. Does the data really show a linear pattern, or does it have more of a curved pattern? So going back to residuals, so here is a scatter plot, and I am just going to draw some dots. Okay, and here's a line of best fit. Okay, could have made it bigger, but that's okay. So this point is the actual value. The predicted value is the one that's on the line. So when the actual value is higher than the predicted value, you have a positive residual, which makes sense. And then if you have a point down here, so there's the actual value minus the predicted value. So that's going to be lower. So that's going to be a negative residual. So that just tells you an idea of what a residual is, how far it deviates from that trend line. And then if you look at a plot of the residual plots look like this. I'll make it bigger. You have this line here. And then you have points, but if you have points in this manner, something like that, that shows a curved pattern or some kind of pattern. When it shows a pattern, it is not linear. This is the residuals. All right, and then we had S. S is the standard deviation of the residuals. It allows us to examine the average prediction error for our regression line, acts almost like a margin of error. And then lastly, we had R squared. R squared was known as the coefficient of determination, and all it is, it's you square your correlation. It is the proportion of the response value that can be attributed to the explanatory value alone. So disregarding other variables, that's what would explain the response variable. So other factors could affect the response value, so it can also be looked at as the accuracy of the prediction equation. And so the interpretation of R squared is the regression line accounts for whatever percent of the variation in the response variable. Okay. Let us do an example of interpretation. Many people believe that students learn better if they sit close to the front of the classroom. Does sitting closer cause higher achievement? So really be careful about this word here, cause. Or do better students simply choose to sit in the front? To investigate, an AP statistics teacher randomly assigned students to seat locations in his classroom for a particular chapter and recorded the test score for each student at the end of the chapter. The explanatory variable in this experiment is which row the students were assigned. So row 1 is the one closest to the front, and row 7 is the farthest away from the front. Here are the results, including a scatter plot and the least squares regression line. So the regression line is drawn for you. The equation is right here. And the values are in the rows. Interpret the slope of the least squares regression line in this context. So the slope, it's a negative slope. So B is negative 1.12 and A is 86. So this is our slope. This is our y-intercept. Okay, so test scores, and the slope is negative, so decrease. So test scores drop or decrease 1.12 points for each additional row a student sits from the front. Okay, interpret the y-intercept of the least squares regression line in this context. So the y-intercept, that 86, is the test score of 86 when the row is 0. Of course, this doesn't make sense because there is no row 0 in the context of this problem. However, if theoretically there was a row 0, you are not going to have any values higher than that score of 86. So that's just the interpretation of the y-intercept. Right. In this section, we will analyze what happens to the slope of the regression line with different samples. We start with a population that we know the data for. We sample many, many times and record the slopes of the regression line for each sample. We analyze the sampling distribution for patterns and relationships. What do we find? So we find that the shape of the sampling distribution is close to normal. The mean of the sampling distribution is close to the true mean of the population. So B is equal to B sub 1, which is equal to beta, which is equal to the mean of the sampling distribution. Okay. The standard deviation of the sampling distribution is close to the actual standard deviation of the population. Okay, given by this equation. From this, we can perform inference tests, which we've been doing since early January. Inference tests are our confidence intervals and significance tests for the slope of a regression line. To do this, though, we have to meet the conditions for the sampling distribution of a regression line. We no longer have 3 conditions, we have 5. So if you look, the random, the normal, and the independence condition are still there. They're a little different, but then you add on 2 more, and that's called the linear and the equal variance. So when I ask you if conditions have been met, you make sure you just talk about each one. So let's go to the ones we already know. So random comes from a well-designed random sample or a randomized experiment. The normal condition, this time it's a little different because you have to make a stem plot, histogram, or normal probability plot, which is the one I like, of the residuals. You check for clear skewness or other major departures from normality. For the independence condition, how is the data produced? Random sampling and random assignment indicates independent observations, and sampling without replacement it requires using the 10% rule. Right, so that covers the 3 main ones that we've been used to. And then there's the linear ones. So let's go ahead and talk about these two. Okay, so for the linear one, the actual relationship between the 2 variables is linear. We analyze the original scatter plot to determine this. And we look to see if the overall pattern is roughly linear, and we analyze the residual plot. Any kind of pattern in the residual plot suggests that the data does not show a linear relationship. Okay, and then for the equal variance, you analyze the residual plot. Is the amount of scatter roughly the same for each possible value of x? And we will do an example where we will look at all 5 of these and figure out if we've met the conditions. So that these are your 5 conditions. Could be a really good multiple choice question on a test. See which one is not being met. Okay, so here is an example problem. Check whether the conditions for performing inference about the regression model are met. And this is going back to the rows and test scores. So going back to our problem. So we'll just start with at the very top. So for linear, if you look at the scatter plot, the regression line has been drawn and it's a weak relationship, but it still has a linear relationship. So the scatter plot has a weak linear pattern. And then look at the residual plot. It has no pattern. If you look at the second graph, so the residual plot has no pattern. So this suggests that the relationship is linear. Okay, for the random, if you look back at the problem, it says the teacher randomly assigns seats. So random assignment, this is an experiment. So we want to establish a cause and effect. So random assignment of seat placement. For the normal condition, this one is not a normal probability plot, but it is a histogram. And if you look at the histogram, there's no, the histogram of the residuals. So the histogram of the residuals shows no strong skewness or outliers. So that normal condition has been met. And then for the equal variance, so we're going to look at the residual plot again. And so looking at the graph, if you look, there's an equal number of dots, even number of dots roughly above and below that line, above this line. And there's even scatter on the left and right. And therefore, that condition is met. So even number of dots, you can say roughly even, above and below, and even scatter on right and left. Here's what you don't want. You don't want something like this. What can I do it? I'll just draw it right here. You don't want this. Something like that. So, and I kind of made, there should be more like that, but you don't want something like that. So, okay. And then finally, the independent condition, the random assignment assures independence. Okay, we are going to do a little bit of 12.1b, the one example where we read a computer printout, and then we'll do the rest of 12.1b and c together in a different notes. So the standard error of slope. Since we rarely know the standard deviation of the population, we alter that standard deviation formula to create a standard error formula. And this is on your formula sheet. So the standard error, it doesn't tell on the formula sheet that it is slope. It just says standard error. Actually, it does. It says, it doesn't say SE, it just says S, and then it has a lower B subscript. And that is equal to the standard error of the residuals divided by the standard deviation of the residuals divided by the standard deviation of the x variable times the square root of n minus 1, where n is our sample size. So this is on formula sheet. S is the standard deviation of the residuals. If S is larger, so is the standard error, which means more scatter and lower correlation. Sx is the standard deviation of the x variable. If Sx is larger, then standard error gets smaller. N is the sample size. As n gets larger, then the standard error gets smaller. Interpreting standard error of slope. How far we expect our slope estimate to be from the truth in repeated random sampling or repeated random assignment. The substitution of the S value for sigma causes our distribution to become a T distribution. So whenever we're going to have a T distribution, we are going to have the degrees of freedom. And the degrees of freedom is going to be n minus 2. So we will look at what the 4-step process looks like and then do a sample problem. So in our 4-step process, in our state portion for confidence interval for slope, we will estimate the true slope beta of the population regression line relating whatever the y value. So your response to your x value, explanatory, at a whatever confidence level, 95, whatever percent. Our plan is to use a T interval for slopes if the conditions are met. So you look at the 5 conditions. So those are your 5 conditions. Random condition, the data are produced by a random sample of size n from a population of interest or group of size n in a randomized experiment. Normal condition, create a histogram, box plot, or normal probability plot of the residuals. So graph. On a test here, just make sure you describe it. Look for skewness or outliers. Equal variance is the amount of scatter above and below the line. The amount of scatter should be roughly the same from the smallest x value to the highest x value. Independence, meaning the 10% condition. All right, and then for the do portion, the calculations, super important. So first thing you want to do is find the slope of the regression line. So remember, slope is b. And in order to do that, you must first calculate. So enter in your list and go to edit, stat, edit, and enter your list, and then calculate the linear regression equation. I don't know if I want to say it's 8, but it's a plus bx is what we want to use in stats. So use that form, and then that'll tell you what the slope is. And then do a 1 variable stats of your x list, and that'll give us and then you can calculate the s. And in order to use the list 3 for residuals, and we won't do this until another section, but I'm just writing this down right now, you need to calculate the linear regression line. So we will do all of this, and I'll show you on a calculator when we get there. 1 variable stats. Oops. L3, we're going to use summation x squared. And then you're going to calculate your standard error. So you always want to pray that you don't have to do all this, because you want the computer printout, because it gives you everything you need and it's a lot faster. So this is the regression output is better, and you want to hope that, and that's probably what you would get. And then once you do all that, you get your information, you're going to compute your T star. And so to do that, you do inverse T, 1 minus the confidence interval, then divide by 2, and then list your degrees of freedom and compute the interval. And here's the interval. B, your slope, plus or minus T star times the standard error. There, your slope. And then conclude, interpret the results of your test in the context of the problem. We are blank % confident that the interval from blank to blank captures the actual slope beta of the population regression line relating whatever your response is to your explanatory. So we will do 1, and we'll just do our rows and test scores 1. Earlier, we used a Minitab to analyze the results of an experiment designed to see if sitting closer to the front of a classroom causes higher achievement. We checked the conditions for inference earlier, and we met them. Here is a scatter plot of the data and some output from the analysis where n equals 30. You had 30 students. So some of the things to read, and we learned this back in chapter 3, but again, we need a refresher. So our constant, this right here, 85.706 is our y-intercept. And our rho, and this value down here, is our slope. And there are some other things that you don't need, but we do need one more thing. I mean, it has the r squared, and then from that you can figure out what r is by just taking the square root of the decimal, but we don't need that. So we need the standard error of the slope, and this is the standard error of the slope. State the equation of the least squares regression line. Define any variables you use. Oh, and I wanted to go back over here when we did our original problem. Our least squares regression line, just dawned on me, would have been y hat equals 0.86 minus 1.12x. Okay, so for this one, same thing, but we want to define our variables. So you can write your equation first using the x and y. So y hat equals, always write your y-intercept first, 85.706 minus 1.1171 times x. And now defining the variables. Well, y hat represents the predicted test score. Equals 85 point. Some students just go straight to this equation, and that's totally fine too, and you don't even have to put the first one there. And then x is your row number. There. B, identify the standard error of the slope from the computer output. Interpret this value in context. So the standard error of our slope is 0.9472. And interpreting there, that, so that's key because, again, students miss interpretations. If we repeated the random experiment many times, the slope of the sample regression line would typically vary, because that's what standard error does, would typically vary by about 0.9472 from what though? Not from the mean, but from the slope of the true regression line for predicting, always tell it in context, so that last little bit is the context part, for predicting test score, which is our response, from row number, which is our explanatory. So this is a really excellent interpretation of the standard error of the slope. And then calculate the 95% confidence interval for the true slope. Show your work. We will estimate the true slope beta of the population regression line relating test score to row number at a 95% confidence level. Use a t-interval for slope. Conditions were met earlier in our notes, so we don't have to state those again. We know from the computer printout, which is our lifesaver, b is equal to negative 1.1171, so that's our slope. Our standard error of our slope is 0.9472. Now it's pretty clear sailing. Now we're going to find t star. So we do inverse t. Right, so it's 95%, so that's 5% left over divided by 2, so that's 2.5%. That would be 0.025. And then our degrees of freedom is 30 minus 2. And that gives us, going to second vars and calculating the inverse t, we will get a t star of 2.048. Now we can calculate our interval. So our interval is our slope plus or minus t star times the standard error of the slope, which is 0.9472. Really easy math. Okay, so here we have negative 1.1171. Well, I went ahead and just calculated it all, left out an intermediate step, which you can do if you want, not a big deal. So our lower bound interval is negative 3.057, upper bound 1.82816. So we are 95% confident that the interval from, and I'm just going to approximate here because I don't have enough room here. So negative 3 to 1.8 captures the actual slope beta of the population regression line relating test score. Oops, can't spell today. To row number. And that's what we'll do for today. And next time we will pick up and do one where we actually have to use our calculator because we don't have a computer regression output. And then we will do a significance test for slope. And then we will be done for the rest of the year. Have a great day, AP Stat students.